right, here we go.
Oh my gosh, can I say something about Can I say something about Ellie yesterday? I was sitting right next to like the court and I hear Ellie like she was like playing defense and then someone after the hair go.
Yeah, I did.
All right, kinetics. We're talking about kinetics here. So this is starting our unit on reaction rates. So rates. So we're going to be dealing with time here. Some event happening per amount of time. Okay. So again, a change in something per unit time. So you're always going to have time as part of your units when you're dealing with rates. So if they're asking you for rates, you're going to have some unit of time in there. And it's going to be per unit of time. So where's that time going to be? On the bottom, right? Because per something means that after the per, the thing's going to be on the bottom. So keep that in mind when you're trying to figure out rates and stuff. In chemistry, we can assume this is substances that we're looking at or a change in reagents. So that's the stuff that you're starting with, your reactants. The mass, the volume, moles, molarity, something's going to be changing. And you use the amount of time based on how quickly that happens. A lot of times it's in seconds, sometimes it's in minutes, but it could be in years, theoretically, okay? So if we had this reaction where we had copper reacting with nitric acid, which was actually done back when we did that Beer's Law lab. Remember, I started with the copper, I reacted with the nitric acid, and then it formed the copper nitrate, and you guys had to figure out the molarity of that. You remember that lab where you had the cuvettes? Beer's Law. Beer-Lambert law. Be specific. Okay. This came out. It was kind of a brownish looking thing. You guys didn't see that. And then there was some water in there too. There would be a way to measure that where we could measure the volume of this NO gas that was produced. So you could do that through water displacement. You guys have done that before. Remember when we did the Alka-Seltzer tablets, you did water displacement there. Not ideal necessarily because some of that could dissolve in water, just like carbon dioxide. You guys saw that on one of your worksheets, I believe. We talked about how certain things would not be a good candidate for that because it's dissolving in the water. You could do a pressure change because you're creating gas here. So you could choose pressure change if you had a sealed container. Molarity, and that's what we did with the Beer-Lambert law. We used the molarity to figure out the colored solution, and then we backtracked and were able to figure out how much copper, theoretically, I started with. Mass lost by the reaction because the NO2, the NO is leaving the container. And then you could also use the pH of the solution because this is being consumed, which is an acid, and not forming a new acid over here. So the pH is going to change. It's going to become less acidic. The pH is going to increase. So those would be different ways that we could measure the rate of that reaction. We could have a pH probe in there, and we could measure as this reaction proceeds, how is that pH changing, okay? So when we are looking at rates, you're looking at a final minus initial divided by the time final minus initial. And it's that change in amount divided by time that's going to give you the rate. Okay, makes sense? These things are going to decrease. These things are going to increase. It is important to recognize, and this is important. So that's why I highlight it in bright yellow. It is important to recognize that you can only do this experimentally. All right? So you have to use an experiment to figure this out. So here is an experiment that they've performed. You can see on this graph that the reaction is proceeding. Our N2O5 is decreasing because that is a reactant. And our O2 and NO2 is increasing because that is a product. This increases at a higher amount or a higher rate. Why?
There's more of it. The coefficient.
This is forming 4 to every 1. Okay? So you can see that this is in a 4 to 1 ratio. The average rate then, and this is where your math skills come into play. Slopes. You guys remember those from math? Okay. All right. Okay, it is. You're right.
It's horrible.
And it is. You're right. But that's why I went around on Monday and made sure that everybody had a TI 84-ish calculator.
I do. It was in her
basement.
Okay. Because I am going to show you how to use your calculator to figure these things out. And then you don't have to use all the calculus and stuff because Lippy never learned calculus and you don't need calculus for AP Chem. So therefore, and thusly, you can use this to get your answers. And I'm going to show you exactly how. But we all need to have these so I can show you. If you have a different one, you can apply what I show you to that and use your own after that. But as far as, and that needs to be done within the next couple days because I'm going to show you how to use your calculator in the next couple days to make that happen. You don't need it for today. Okay. So average rate of reaction is found by taking the difference in the molarity over the difference in time. You can use those small changes to get an instantaneous rate, which is the same as the slope of the line that is the tangent to the curve at a particular time. The initial rate then is whatever you started with. All right. Now we have something called a collision theory. The collision theory then is in order for a reaction to take place, you have to have 3 things happen during that process. Okay. The particles have to collide. They have to be lined up right so that they hit properly. And you have to have energy greater than the activation energy available. If any of one of these 3 things doesn't happen, you're not going to have a reaction. Okay? There are things that can affect these. Reactant concentration. So the more you have of a reaction, the more likely these things are going to collide. It's kind of like in the hall during passing time. You're pretty likely to hit somebody out in the hallway when you're walking during passing time because the concentration of people out there is high. You are much less likely right now to go out and walk in the hallway and hit somebody. Okay?
That's not true. When I go down the hallway, I just like people. She forces her will.
Temperature. Higher temperature means that you are more likely to have particles to collide with that energy that's needed to go past this activation energy. So the higher the temperature, the more likely you are to have this. The surface area then, if solid particles or something that forms an interface like an immiscible liquid or gas have more surface area, then they're more likely to be able to have them collide. Okay. So a small a sample that is broken up into many, many little pieces versus a big chunk of something, the smaller thing is going to have more surface area by volume than the one big chunk. And that's hard to conceptualize.
What does immiscible mean?
Immiscible means that it doesn't mix. Okay. So, oh shoot, is this not going to let me write on it today?
What is an interface?
Where they touch.
Standard. Hey, I only had half a year going.
That was a month.
Seriously?
I'm not gonna do it.
Oh, because of COVID? Oh, okay.
No, we just transfer it to us.
All right. So if you have something that has a bunch of little pieces like this, and you collectively go through and you add up all of their surface areas versus something that would have come from like this, the surface areas of all of these combined is going to be greater than the surface area of this one chunk, because the majority of those particles are going to be inside the middle of this. Okay, so breaking something up is going to give it a better chance of colliding with this material. Does that make sense? Mm-hmm. All right, catalysts then are going to speed up chemical reactions. Okay, you studied these. If you had AP Bio, you probably studied catalysts. You probably studied a lot of them. What did they call them in AP Bio? Enzymes, exactly. Okay, so catalysts, enzymes are catalysts. Okay, and what they do is they are going to do a couple different things. One of the things that they do is they provide an alternate pathway to a reaction. And what that means is it's going to change the reaction in some way that it's going to lower this activation energy. In certain cases, it will take a one-step reaction and break it into two different steps. And we'll talk about that as we move through this unit. Because honestly, guys, we've kind of misled you in the process of understanding some of these reactions. When we write these reactions down like this, we're showing you the complete reaction. We're showing you what you started with and what you ended with. But honestly, most reactions take place in several different steps. You have what's called elementary steps, where you have a reaction that looks like this, but it's actually taking place in a couple of different steps. And we're looking as the whole reaction here, we're looking at what we started with and what we ended with, but we're not looking at the changes or transitions that happened in between. So we're going to be talking about those in this unit. One of the other things that one of the other types of catalysts, so this was a homogeneous catalyst, okay? That means that it's in the same phase as your reactants. Heterogeneous catalysts then are in a different phase. They're going to alter the orientation of the molecules. So they're changing this orientation so that the molecules are more likely to collide and you're going to have more effective collisions. Okay. So other environmental factors also can affect that, but these are primarily the ones that they look at in AP chemistry. Okay. So chemical kinetics, when we talk about that, again, we're looking at these factors: physical state of the reactants, So gases are more likely to react faster than solids, say. Okay? Because gases are spread, you've got them here, and they're more likely to form those collisions than, say, a solid that's sitting at the bottom. It also tends to have a smaller particle size versus your solids that are typically going to be in a big chunk. Concentration of the reactants, temperature, and then the presence of that catalyst. So physical state, the more readily the reactants collide, the more rapidly they can react. So the easier for those to collide, the more active this is going to happen. So when a solid reacts, only the particles on the surface of that solid are available for the reaction. If the solid is broken up again, then the surface area is going to get larger and you're going to have more particles available for that. Homogeneous reactions, where everything's in the same phase, is often going to react faster as well. So if you have everything that's all gas or everything that's all liquid, they're going to tend to react faster. Heterogeneous reactions then, where they're in the different phases, involve solids. If they're increase their surface area, then you're going to end up having those react faster as well. And we already talked about surface area. Concentration then, increasing the reactant concentration is going to increase that reaction. So more molecules equals more collisions. And like I was saying, that a good example of that is walking out in the halls. Okay, except for Allie, of course. So similar effect is observed when we increase the pressure, we're reducing the volume. So if you increase the pressure and you're dealing with gases, then that pressure is going to force those that material closer together. It's going to change the volume, reduce the volume, and make that more likely to collide. Squeeze people into a smaller room, they're more likely to collide. Temperature then, the reaction rate is generally going to increase with increased temperature. Your kinetic energy then is related to that temperature. At higher temperatures, you have more molecules moving more quickly, which is going to increase those collisions. So if you think about that in terms of like a Maxwell-Boltzmann distribution, if you're at a higher temperature, you have more molecules that have acquired the activation energy that's necessary for that reaction to occur. At a lower temperature, you're going to have fewer of those molecules. That's the blue stuff down here. You're going to have fewer of those molecules to be able to go through that reaction. Does that make sense? They just don't have the speed to make it happen. Okay, so that's what this slide is talking about, where you're just not going to have as likely of those collisions to occur. And then again, the catalyst will look at the overall balanced equations. They don't contain a catalyst. They don't show you the catalyst. So because of that, sometimes they will show it like in biology class, they'll show it where they have like an arrow. So on here, they'll have like your yield sign, and sometimes they'll show it coming in like this. They'll have a catalyst listed here. We don't do that really in chemistry. But I'm going to show you how to be able to identify catalysts as we move through here. Okay. Does this make sense as far as one of the things that I missed on the slide here was talking about this orientation. Does it make sense as far as the orientation is concerned, what I mean by the right orientation? So if you have like, let's say that you've got a molecule here and you want to react this guy right here with something like this, and you want to form, let's say that we want to form this guy and this guy and have this and this. Okay, so we're taking these two things and we're forming these two things. All right, if we come in and this guy happens to hit this guy right here, there's not going to be a reaction there because we're not forming solid blue with red circle, red clear circle. Okay, these have to hit the right way. Is this going to let me erase? No. I'll figure it out. We have to hit the right way so that this is lined up so that when, when this hits, this blue hits the red and this guy hits this guy right here to form these. Okay. So it's kind of like, you've got to make sure that you hit it the right way to make that happen. And the more stuff you have of these, the more likely that collision is going to occur in the right orientation to make that happen. Does that make sense now? Okay. All right, I do. So, student, I like his name, yeah, wanted to figure out the rate of a reaction by measuring the rate of CO2 gas that was formed between HCl and calcium carbonate. According to this reaction, which happened, which set of conditions will cause the reaction to go slowest? Okay, small chips, I'm buying that. Yep, this guy, the molarity is less. And if we could put it in an ice bath, okay? So small chips is bigger than powder. So if we could have these three things occur, that's going to cause the slowest conditions. And then I'm guessing you know what's going to cause the fastest, right? The things that's not circled here. Does that make sense? Why?
Wait, so do you want a small surface area or the biggest surface area? Powder.
Powder's going to have more surface area because these are chips. These are powdered. Like this is teeny, teeny, tiny. Like you could count the chips. You couldn't count the powder molecules or pieces. You wouldn't want to. Okay?
I need that slide. You can wow.
Alex, her butt's flat.
It's just square. You're so good. That's about I'm a bunch of nerves in the light. Do you think if I run out with me? Or you just have to sit on the bench right away? Oh wait, I'm there.
What is
I
it?
know.
What is this?
Just gonna have to reset it. The rest, I'm not
It's where we
sure.
used to sit there and
Little love to talk.
Well, no, today you're going to try to look
No,
at
it's
myself
there.
for once.
It's there. Tell me that you never shut.
We did one.
Lil talked for like 10 minutes straight.
Because nobody shut me up. So I'm just
Oh my God, Lil.
this time I'm gonna try to stick to shape.
Did you know that Lil?
But 9 times out of 10, people do their back sometimes.
What are you saying? She like does her
Is
like.
it high pitch?
Yeah.
I don't know.
Lil talking seminars.
Are you guys even trying the problem? So if this is the rate of disappearance, the rate of the appearance would be what?
The same, just positive.
It would be positive, but
Oh.
So it's going to be positive because we're appearing. That's our here. Exactly. Matthew, my goodness, you were on it today. So 2 moles of O3. That's here. And 3 moles of O2. Yep. 0.0051. And that's big M over S. Now, you will sometimes see this written for units. So get used to this as big M S minus 1. Okay? This is that. It's the same thing. Be careful because that will happen.
And it like kept like not hot, but it like I don't know. It's like where you can feel it. Yeah, and I was like, oh, what a weird thing. And now it like hurts. Oh, what a weird thing. Okay, that doesn't sound good if it's in the car.
So this is the disappearance of my ozone. Okay. And we're talking about reaction, so we're going to change that to a positive value. We're getting it out of just here, and we want to know moles of reaction. So for every one of these consumed, we've run through the reaction 1 time. So the moles of reaction here, done, is going to be okay, or we can write this.
How that's set up is for an extra reaction, you always say to put that in the molarity. Always say those times the 1 mole. That's how many.
Yep, because and your moles cancel here, and it's going to keep you with the same
And
units.
you always use the coefficient of the reaction.
Whatever they've given you, they gave you ozone, so that's what we're using here to get to the reaction.
So they gave you oxygen, and you would
Yep,
use that.
and then this would have been already a positive value,
What's 1 mole of reaction?
or this would have been oxygen, but yeah.
You always make it positive.
Guys, one whole day is dedicated to water.
If this is a reactant, yeah.
Yeah.
Thank you.
You're welcome. Sorry that it took so long. I just forgot to, So, all right. So homework tonight is 5, 3.
You're gonna be one of 2 people that I get something from. So
Oh no, you'll get it from more people.
No,
I just need
I never
to.
do.
You just need to be reminded. So,
You don't know what normally happens, do you?
well, I do, and that's why I made sure that I got you what you needed. So,
Yeah. Remember this fall when we collected for Chorus and Charlie left?
mhm.
If I told you what the grand total for those